first of all, thanks everyone for joining us today for what should be a really interesting webinar. Now, I'm Karen Shaw, I'm the client manager for the municipal industry in Australia and New Zealand. I've probably met or spoken to most of the people that are turning up to today's webinar. I'm a water engineer and have been for over 25 years with a passion for resource recovery and sustainability in water treatment design. And I believe the technology that we'll hear about today is very interesting and particularly relevant for Australia. Every day in our industry, we hear water referred to as drinking water, potable water, non-potable water, reuse water, environmental flow, river water, but in reality, all of it's just water. And it's our duty as custodians of water when we borrow it from our planet's water cycle for our various purposes to ensure that we do everything in our power to make it safe for ourselves and our environment. And in that knowledge, we should certainly be looking at ways to remove micropollutants we know are entering the water cycle through our human activity. Micropollutants, which include pharmaceutical waste products found in our wastewater, when not removed effectively, can have a very negative effect on the quality of our drinking water and the environment. Now, our wastewater treatment plants are our primary barrier in our fight to control the spread of micropollutants into our water cycle. And we already have quite a few processes like advanced treatment processes, activated carbon absorption, advanced oxidation processes, and membrane processes, which can achieve some level of micropollutant removal. However, the technology we're going to hear about today is not a chemical or physical process. It's a biological process, which is interesting as it can be more sustainable approach to the treatment. The eXeno process you'll hear about could either replace or work with some of the more traditional chemical and physical treatment processes to provide overall a more sustainable and cost-effective method of managing the micropollutant risk to our water supply. So on that note, I'm going to hand over now to my two colleagues, Fernando and Brandy. I'll let Brandy introduce herself and Fernando, and then they'll take you through what I hope will be some very interesting slides about our eXeno technology.
Fantastic. Thanks for the introduction, Karen. My name is Brandy Nussbaum. I'm the sales manager at AnoxKaldnes. And AnoxKaldnes is a Veolia Water Technologies company. Of course, we're one of the technology centers of excellence, and we're located here in the south of Sweden. And I'm joined also by my colleague, Fernando.
Hello, good morning, everybody. My name is Fernando Morgan, and I work as Technology Strategy Manager here at AnoxKaldnes. So we will start by highlighting some general aspects on micropollutants and how biofilm technologies, specifically the one that AnoxKaldnes has been commercializing for more than 30 years, the NVBRs, can help to address the contamination of these pollutants in wastewaters. So, micropollutants, I think we all have heard about them. They are referred to as organic micropollutants or emerging contaminants, and they are, as the name indicates, they are present in very low concentrations, relatively low concentrations in the range of nanograms to micrograms per liter. However, despite these low concentrations, they do pose risks into the environment and to living organisms because they, some of these compounds are toxic, persistent, and they tend to bioaccumulate. Our focus for today is the fate of these contaminants in wastewaters, and specifically in wastewater treatment plants that are treating municipal wastewaters. There is a lot of, now we understand how or where these micropollutants end up in our wastewater treatment system. And you can see here on the left-hand side of the slide is the main sources, but it is interesting to note that it's not actually the producers of these chemicals or even the main users in a more intensive way as hospitals that are the main polluters here or the main sources of contaminants going into a municipal wastewater treatment plant. It is actually us, the consumers. And this is an interesting aspect because we bear responsibility actually for most of those micropollutants that are arriving into a wastewater treatment plant. And it is the use, of course, of a cocktail of contaminants now, we can say, but a cocktail of chemicals that we use for different purposes, especially medicines, drugs that we do not use completely, and then we think we excrete into the water that arrives into these treatment systems. The good news, as you will see, is that the treatment systems available now, they can handle already part of those contaminants. They can remove a significant fraction of those contaminants. However, due to the risk that these compounds pose at relatively low concentrations, that's not enough. We need to apply further treatment in order to remove them at concentrations that may not be so risky for us and the environment. We are talking about a cocktail of compounds, as I indicated before. In this slide, we have just highlighted some of them, and mainly medical chemicals, medicines, medicaments, drugs. And you can see here that there is a wide range of them, anti-inflammatory ones, antidepressants, antibiotics, blood pressures for controlling blood pressure, but also other chemicals that are used in the medical industry, X-ray contrast media, for example. And of course, there are pollutants that are coming either from their manufacturing sites directly as industrial pollutants, or other chemicals that have different applications like pesticides, herbicides, but also different personal care products could be, such as beta blockers against UV. And all of them are present in wastewaters. They have different properties, and we are going to be talking today about biological removal of these compounds, and the removal of these compounds by means of microorganisms will depend on their properties. And therefore, there are these different cocktail of pollutants have different biodegradabilities we can indicate. So there are different technologies. Karin mentioned some of them, specifically physicochemical technologies that can be used for the removal of these micropollutants. In this slide, we are highlighting the general technologies that can be used, but we are also highlighting the trademarks of some of these technologies from Veolia Water Technologies. But fundamentally, it is the same. We have on the left-hand side indicated the physicochemical treatments that are actually the ones that we think first about. They have been studied for a longer period, and then in a way we can consider them as conventional technologies for treating these micropollutants. We are talking about techniques or technologies that treat pollutants by absorption mechanisms, such as activated carbon that could be granular or powder, the GAC or PAC that you may have heard, or by direct oxidation of the compounds by strong oxidants such as ozone, or combination of these technologies. And membranes also play an important role here, but ultrafiltration, nanofiltration, and reverse osmosis. But today the focus that we will have is on biological removal, specifically using biofilm technologies, as I indicated before, the moving bed biofilm reactor, the mbbr. And these technologies allows us to even talk about hybrid technologies, the combination of biological treatment with physicochemical treatments that, as we will see, will have or can have advantages for the treatment of these micropollutants. So, as I mentioned before, the origin of these micropollutants can be traced back to obviously industrial sources, such as the pharmaceutical industry, where some of these products or chemicals are produced. Hospitals, where they are intensively used. And we have worked with wastewaters from this sector over more than 30 years, providing solutions for the removal of pharmaceuticals or treating the effluents from the pharmaceutical industry. Today, we will be talking about how to handle these micropollutants at relatively lower concentrations from municipal wastewater treatment plants. And we have been working for this already for several years. And here we have highlighted for you that it has taken some research and development, well fundamented with the collaboration of universities, especially here in Scandinavia, in Denmark and Sweden. Scandinavia is following Northern European countries such as Germany and the Netherlands in leading the implementation, development, and assessment of different technologies for the removal of micropollutants, and really leading the example, or following the example, sorry, of Switzerland. Switzerland is the first country that has some level of regulation on micropollutants here in Europe. And legislation will come, but we don't have any specific legislation, at least in the European Union yet. So, for those that are not or may not be so familiar with NVBRs, here we wanted to show you some of the components and how basically it works. We have our reactor volume in a tank, and in this volume we have plastic carriers or plastic elements that we call biofilm carriers or media, upon which biofilm develops. Biofilm, it's a way for microorganisms to grow attached to a surface. These give them certain characteristics and properties and advantages as well. They can be retained in the system by growing on these carriers, since we use sieves for screening the water that is treated and retaining the biomass in the reactor. This gives advantages to mbbrs. The process can be more intensive, more efficient in terms of how much biomass, microbial biomass that is in charge of removing the pollutants, can be contained in this volume. The carriers are moving around the whole volume of the tank, and by means of these, they are removing all these pollutants. We can have different processes for removing the pollutants under aerobic conditions, providing oxygen, and for this we need an aeration system that can provide that oxygen for the microorganisms to degrade the pollutants under aerobic conditions. But this aeration system also provides mixing capacity or aeration-based mixing for these carriers to move around in the volume of this reactor. If we are not having an aerobic system, we can have anaerobic conditions or anoxic conditions, anaerobic without oxygen, and anoxic conditions without oxygen, but with the presence of other compounds that can be used as electron acceptors, such as nitrates, for example. But when it comes to wastewater treatment, municipal wastewater treatment, I'm sure you are familiar with activated sludge. This is the biological process that is mostly used for wastewater treatment around the world. But when we look at how to implement mbbr technologies for municipal wastewater treatment, we could highlight two main approaches that are illustrated here. First, a pure mbbr process, in which we have the mbbrs that I explained, mainly taking care of the treatment. And that means that we have the microorganisms mostly growing on biofilms, as you can see an illustration of a carrier, or the picture of a carrier with some biofilm growth on it. But we can have another way of performing this treatment, something that is called IFAS, Integrated Fixed Film Activated Sludge. And this is a combination of having activated sludge. As you know, in an activated sludge system, we have the microorganisms growing in suspension, forming something that is called flux. These are aggregates of microorganisms that are in suspension in the system performing the treatment. So we can have that activated sludge with an mbbr that is carriers that have biofilms. And the combination of having these two types of biomass gives certain characteristics and advantages to the process. Specifically, it is very advantageous for nitrification in activated sludge system plants, especially for retrofitting and making these plants more compact. So as I mentioned before, one of the aspects that that differentiate NVBRs from conventional activated sludge is the fact that we are growing these carriers on biofilms, and we can retain those carriers with biofilm in the system. That means that we can uncouple their hydraulic retention time from what we call the sludge or cell retention time. And that allows for this biomass to have very long retention times in the system, and that can provide them for an opportunity to become very specialized. This also improves the efficiency. We have a better removal or a higher removal of these contaminants per volume of reactor, because we have more biomass in that volume. And by having biofilms, we give robustness to the system. Biofilms, microorganisms in a biofilm, microorganisms tend to be embedded in something that it's called extracellular polymeric substances, and these are polymers that are excreted by microorganisms, and these polymers help them to stick together and to attach to the carriers. By doing so, also provide them with a way of being more resilient to variations in toxic compounds, for example, or other variations in the operating conditions of the reactor. So when we talk more about micropollutants, we wanted to give you some examples on what is understood so far. Here in this graph, we are showing results from a study that was conducted in Denmark at pilot scale, treating the effluent from a hospital in Denmark. And the interesting aspect here is when we look at how a regular activated, conventional activated sludge will treat the micropollutants with respect to a biofilm process, an MBBR process specifically, with the two that I mentioned. In purple, we have here the pure MBBR, and in light blue, the IFAS. HIBAS is the trademark from us. We can see that there is, can you press the next one, Brandy? There is a difference depending on the types of compounds that we are looking at. For easily degradable compounds that are on the left-hand side of the graph, we see that the predicted removal is not significantly different to what happens in a conventional activated sludge system when we look at MBBR processes. However, the difference is more significant when we are talking about compounds that are more difficult to degrade. As you can see here, compounds with a medium biodegradability or that are really difficult to degrade. One of these compounds, interestingly, is diclofenac, which it is this anti-inflammatory drugs that we use. And although not completely removed, it is removed at higher efficiencies using a biofilm system than an activated sludge system. We have confirmed these results also from full-scale evaluations, and actually third parties have also done this. This is also to give you a highlight here on a study that was performed in the US, looking at, they evaluated 6 plants where they have MBBR processes, specifically the IFAS process. And specifically from these plants, there were several ones that had actually Veolia water technologies processes, such as the HIBAS with different carriers for the MBBRs. And in the table, you can see, I highlighted on one side the IFAS results from the conventional activated sludge results, and the authors highlighted some of the compounds. There is a long list there for which the removal was higher in the MBBR-based process. So there is definitely evidence indicating that biofilm processes, such as those ones employed in MBBRs, lead to increased removal of these micropollutants in wastewater treatment plants. But this is looking at how a wastewater treatment plant treats these compounds. NVBRs allowed for a flexible process solution that can be implemented. And the way we do this is by staging different reactors in series generally, because this gives certain advantages to the treatment. By doing so, we can specialize the reactors by selecting microorganisms that are staying in these reactors for a long time, and they can be acclimated or even being selected for the removal of those specific compounds, from the easily degradable to the more difficult to degrade compounds, as illustrated in this slide. So this is a feature that we can achieve with NVBRs for the removal of these micropollutants. So to give you more results, a little bit of a teaser in how this technology works. It's not only applying the biofilm in general, but how you implement this biofilm in the MBBR can also have impacts on the removal of micropollutants. One of the latest developments in terms of MBBR media from AnoxKaldnes side has been the Z carrier that is illustrated here on the right-hand side of the slide. This is a very unique carrier that has the shape of the saddle shape that you can see, and on both sides we have a grid that consists of a bottom area surrounded by a grid of walls that we can say, and in these squares we have the possibility to grow the biofilm. The grid can be different, and we can control the height of that grid, of those walls around those squares, to different heights. The heights could be, and here we have an illustration in this graph, from 50 to 100, 500 microns. That means that the biofilm can grow up to that thickness or height. By doing so, we can control the maximum thickness of those biofilms in these systems. One of my colleagues, Elena Torresi, who was involved in the development of these technologies for the removal of micropollutants with NVBRs, evaluated how this biofilm thickness can have an impact in the removal of micropollutants. And what she observed was that thicker biofilms allowed for a more overall efficient removal of micropollutants. You can see here in this graph the three different thicknesses, and that in general, those that are thicker tend to have higher removal constants. The higher these rates, the higher the removal. However, by having thinner biofilms, you could have a higher removal of specific micropollutants. Here on the right-hand side of that graph, you have TCF, diclofenac, this very difficult to remove compound. But it was interesting to see that when you have thinner biofilms, perhaps a more selected microbial community present in that biofilm, this was more specialized for the removal of that compound. And this is interesting because they can offer us ways of engineering these MBBRs with perhaps a combination of these carriers to target very specific removals of these compounds in these systems. And the next slide is an opportunity for you to ask questions. And I can see that my colleagues have already put some questions there. So the first question, please write your questions if you have more, but I will start here. Why do biofilms provide for better micropollutant removal? Yeah, this is an interesting topic. It has been addressed in the research, and although not 100% understood, what is understood is the following. First, biofilms in this type of MBBRs allowed for a long retention time and the specialization that we indicated. One interesting aspect is that the microorganisms that are involved in the removal of these micropollutants are related to nitrification, the process of converting ammonium into nitrate, but specifically into nitrites, the ammonium oxidizing organisms that require that have a relatively slow growth. They tend to be attached in the biofilm because they require longer retention times in order to thrive in these systems. And these microorganisms have been related to the removal of micropollutants, and they tend to grow in this on these biofilms. This is one explanation. And also likely perhaps that resilience that we discussed before of being more somehow protected in the biofilm. But this is still a topic that needs to be further investigated in general. Another question, why micropollutants, these can micropollutants be removed also anaerobically? Yes, we mentioned aerobic conditions. We haven't gone into details. Yes, micropollutants, researchers have indicated the removal of micropollutants under anaerobic conditions. However, there is agreement in that aerobic conditions leads to higher efficiencies of removal of micropollutants. So the technology that we are actually presenting to you is really under aerobic conditions with the use of oxygen, because it is more efficient. Aerobic conditions are more efficient than anoxic, and anoxic more efficient than anaerobic conditions. Another question, the Z carrier doesn't appear to have holes like normal biocarriers. How does biofilm grow them? Yeah, I tried to explain that they have this grid, and there is a volume in this grid, squared volumes, and this is how the biofilm grows. So it is protected by the walls of those grids on both sides of the carrier. But the fact that the biofilm is exposed on both sides of the carrier to the bulk liquid gives specific characteristics to these mbbrs in comparison to other conventional carriers, in which you have the protected biofilm more in these holes, as in the question, but those holes may be clogged eventually also, and that perhaps make this system not as efficient. I don't know if there are other questions at the moment, Brandy, that...
Okay, seems not. So we will continue the story of eXeno and micropollutant removal. So Fernando has sort of set the stage here. He's put a good background for us, and you're now fully armed with the information that these risky compounds can be removed biologically, and specifically with the use of biofilms and mbbr technology. mbbr technology, as probably many of you know, has been around now for more than 30 years. We apply it in many different ways across wastewater treatment plants, both industrially and municipally. But what we want to share with you now is how we envision this eXeno solution being applied for specifically micropollutant removal. So I'm going to start first on the right-hand side of the slide, where we show a municipal wastewater treatment plant followed by ozone for micropollutant removal. As Fernando explained, it's a physical chemical process that has been used already for micropollutant removal. But then this ozone step, it actually produces some transformation products as well as nitrosamines. And so we follow the ozonation step with a polishing mbbr to remove those byproducts and those nitrosamines. We actually have a couple of full-scale references of this configuration, and I'm going to share more details on that in just a few more slides. So now let's actually have a look at the left-hand side, where we see a similar setup, with the exception that now you have an eXeno mbbr ahead of the ozone step. And this is so that some of the micropollutants can actually be removed biologically, or at least reduced biologically. And by using this biological step, you'll see that relatively the size of the ozone step is reduced. So by being able to remove some of those micropollutants biologically, we're able to reduce the ozone step, which is of course a savings in footprint, but the bigger savings of course comes on the OpEx side and the regeneration of that ozone as it ages over time. And then of course, similar to the right-hand side, we follow that ozonation step with a polishing mbbr, again to remove the transformation byproducts. We're now going to zoom in and take a closer look at the implementation on the left-hand side. So this is the slide that I just talked about, where we have eXeno followed by ozonation, followed by the eXeno polishing mbbr. We've already explained the advantage that biofilm has for micropollutant removal, but in order to maintain a healthy, strong, and diverse biofilm, as Fernando explained, the importance of that, it needs to have some sort of periodic exposure to a higher strength influent, because we've already talked about that these micropollutants are present in very, very low concentrations in the wastewater treatment system. So basically what we do is in order to target these low concentrations of these complex compounds, we use a bypass, or we change the flow pattern to sort of give the biofilm a chance to sort of bulk up, if you will. It's like a steroid shot for the biofilm, if you think about it like that. We depict it here by showing 3 reactors, but don't get hung up on the number of reactors or all these arrows going around here and causing confusion. We're just simply showing that by changing the flow pattern and changing the way that the influent is introduced, and by having a periodic bypass or change of that flow pattern to bring in some higher strength influent, we're able to maintain a more active, healthy, and diverse biofilm, which is going to help us target those very complex compounds and those compounds that are present in low concentrations. It's also very good to note that in this configuration, we also target tertiary nitrogen removal. So, in most cases in a wastewater treatment plant, you may be getting down to less than 5, maybe less than 3 milligrams per liter of ammonia in the normal biological step of your wastewater treatment plant. As those limits continue to be pushed lower and lower in places around the world, this is also an advanced way to get sort of some polishing of that remaining ammonia in the system. So in fact, we actually use this alternating flow pattern in tertiary nitrification plants already in operation. This is an example of a plant in the UK where they have very strict discharge limits and actually spot sample analysis for ammonia. So in this case, the plant is designed with 2 mbbr reactors in series, but the flow is changed periodically to change the position of the 2 reactors. So the flow is just rotated so that periodically one reactor sees the higher strength influent from the wastewater treatment plant, and then we change again. And in this way, we're also doing the same as I tried to explain in the previous slide. I hope it was clear enough that we change this flow pattern to introduce a higher strength influent to, maintain a higher productivity of the biofilm, a healthier biofilm, and a stronger biofilm. So this basically means that each of the reactors gets its turn to be in position A and therefore receive the high strength wastewater. There are a number of plants already in operation like this, specifically in the UK, where they have these very strong ammonia limits. So it was kind of our idea as we were developing the eXeno that it's probably very likely that these plants are also getting some latent micropollutant removal by the fact that they are a biofilm plant. They are an mbbr, meaning that they're a biofilm plant, but they are also operating in this unique flow pattern, which also, as we have seen, enhances the micropollutant removal. So these plants, or this plant that I'm showing you here from the UK, was not specifically designed for micropollutant removal, so keep that in mind. But we did do a sampling campaign to just have a look. And we looked at 23 targeted compounds. Of those 23 targeted compounds that are common indicator compounds, we found 11 of them. So the system actually achieved varying removal percentages of these compounds, but do remember that it was not specifically designed for this. But what this testing campaign does is it really further validates that changing this flow pattern and giving that biofilm this sort of steroid boost really does enhance the ability to biologically remove the micropollutants. So now we're going to zoom in a little bit on from a few slides ago on the right-hand side of the screen, where we have an eXeno mbbr polishing step following ozonation. As I promised, we do have some full-scale installations of this, and I would like to tell you about that. So the first full-scale installation of eXeno for polishing after ozone is in Warburg, Germany. So Germany just happens to be one of the countries that has taken some advanced steps without regulation to start targeting micropollutant removal, especially at plants over a certain PE. Mainly we have focused, mainly they have focused on physical chemical processes like ozone and activated carbon. But as we've discussed, the presence of ozone actually does create another problem in itself by the production of these transformation byproducts and the nitrosamines. And in this case, the polishing mbbr was put there specifically to tackle the challenge that comes from the ozone. So the early results from this plant have been published again in papers done by a third party, and you're welcome to dig into those later on. But in summary, the polishing eXeno step removes about 95% of the compounds that come after ozonation. We're very excited about these early results. We definitely see a growing interest in this configuration because as Fernando explained very early in the presentation, physical chemical processes already have a history with micropollutant removal. So there are already implementation of this worldwide. And this is a chance for us to come in with our biological solution and help solve the problem of the transformation byproducts and the nitrosamines. So just before we head to the conclusion, I would just like to take this moment to remind ourselves why this is important. Karen did a great job of setting the stage for that and hitting us all right in the heart with why this is so critical. I mean, healthcare continues to advance, right? We all know this, and it provides immeasurable benefits in our lives. But the cocktail of medicines and personal care products and other compounds that is arriving at the doorsteps of our wastewater treatment plants, it poses a huge threat to the environment and to our drinking water systems. Even without regulations, we can begin to address this issue by raising public awareness, by being aware ourselves and raising public awareness. As wastewater professionals, we can continue to educate ourselves about the risks and the solutions so that we are prepared to handle them when the regulations are in place. So thanks for joining us today for this introduction to biological treatment of micropollutants. Biofilms, and specifically mbbr, are powerful, and we have the tools to design them in ways to achieve the types of treatment that we want. We at Veolia Water Technologies fully believe that the future solution for the removal of these compounds should include a biological step. As Karen fully led us at the beginning, it's more environmentally friendly option, it's more sustainable, and for sure it will save CapEx and OpEx on the physical chemical solutions. I will just wrap up by saying that what we did here today is a very short introduction. It's the result of years of research, so there is definitely a lot more to this story. And we would be happy to discuss that in more detail with you. You can contact Fernando or I directly, or for your local contact, of course, you met Karen at the beginning, and she would be happy to hear from you as well. Thank you very much for your attention, and I think now we'll have a look and see if we have any other questions. I see a couple questions have been populated here. The first question is, if I understand correctly, eXeno is an mbbr system. Do you have other experience in pharmaceutical removal? That's actually a great question. And just to give you a little bit of background, for sure, AnoxKaldnes, who has been working with mbbrs now for 30 years, more than 30 years, has a long history treating pharmaceutical wastewater from pharmaceutical production. We have something like 25 or 30 full-scale references in the pharmaceutical industry. And these would be treating these same types of compounds only in macro concentrations, so in milligrams per liter instead of micrograms per liter. But we see the same phenomenon as Fernando was explaining, the need to maybe have multiple reactors, or at least to drive the biofilm to be diverse enough to tackle that set of complex compounds that are in the wastewater. It's the diversity and the strength of that biofilm that help us target this complex cocktail, as we sometimes call it. So that we do have a lot of experience directly in the pharmaceutical industry, and we're taking what we've now learned, over those 30 years and bringing that to the micro level as we're targeting these compounds now in micro concentrations. The next question is, do you have any full-scale references of the eXeno M solution? If I understand the question correctly, this is probably what you mean is that if I refer back again to the left-hand side with this rotating flow pattern, this changing with this bypass. No, we don't have any full-scale installations of that yet. As I mentioned, we have similar types of installations for tertiary nitrification, being especially in the UK, especially, but in other parts of the world. So the concept is in place, but not specifically for micropollutant removal. Now I'm going to have a look here and see if there's some other questions that have popped up. Let me just have a look here. There's a question here. With no framework for micropollutant removal, even in developed countries, what is the rationale behind applying basins for maintaining complex bioculture by specialization and ozonation? Yeah, I'll see if I understood the question correctly. Maybe you see it differently, Fernando. But if I understand the question correctly, is that there aren't any regulations in place, so why are we looking at this now? I'm not sure if I completely understand the question, but yeah, you're right. There isn't a lot of framework regulation in place, other than in Switzerland, as Fernando said. But there are a lot of countries, especially what we see around Europe, who are already advancing on this through national initiatives. Sweden, Germany, as I mentioned, of course, Switzerland. We're starting to see them already starting to address this on a national level, especially with plants over a certain size. And we know that eventually these regulations will come, which is why we want to get this information out now to give you the tools to be able to evaluate possible solutions for your plants in the future. Fernando, I don't know if maybe you had saw it a different way.
Yeah, I understand perhaps the question, what is the rationale of how do we perhaps evaluate the systems? There is no regulation, but then how are we evaluating the applicability of either of mbbrs or ozonation? Perhaps let us know if we don't answer, but a comment on this is that yes, there are, as you can imagine, many of these compounds. So what to target? How do we target the efficiency? The next there is a second question also: is there any control of the process to maintain a certain percent removal? And it addresses both. So what I know from this Swiss regulation, they have targeted specific compounds that are for the removal that they consider representative. That I think it's up to, I don't remember the number, but it's not more than 20, perhaps around 10 compounds or 15 compounds. So in the studies that we have performed, my colleagues have performed, and similarly other studies, they target representative compounds from the different types of groups having different chemical structures. In the case of my colleague Elena, she was working with 23 compounds representative from all these different types, and that have, she had beta blockers, some carcinogenic compounds, pesticides, anti-pregnancy pills, etc. All these compounds present, and this is how the evaluation is conducted. Some of them are more easily degradable, others are less, are more difficult to degrade, and the evaluations are based on this. So this is part of the complexity, and let's see how regulation develops and what they will use for those regulations. Perhaps they will follow the Swiss model, but from our perspective, when using biological processes, we also need to understand what this biological process can remove, because the removal based on ozone or activated carbon is different due to the different technology and the way this process works than biological processes. Other way of assessing perhaps the removal of these compounds could be with more generic testing, such as ecotoxicity tests, tests that target not the specific compounds, but the effects that all this cocktail of compounds may have, and seeing if we apply these technologies, whether it is ozone, activated carbon, or biological process, we remove that toxicity, for example, or that or the impact that these compounds altogether may have. That's another way of evaluating it. We haven't done so many studies on this, or we haven't done those studies actually at all. But this is also something that is being discussed in general for the removal of micropollutants.
Great, because and now that's a perfect lead-in, Fernando, actually, because the next question was about the control of the process to maintain removals. And I think that what you have said there more or less answers the question, because it's true that that these micropollutants there can be hundreds of them, and it would be impossible to expect wastewater treatment plant operators to monitor a huge complex set of compounds leaving their treatment plants. And that's why I think that's why there's some challenges with developing the regulation is which compounds are we going to look at, which compounds are we going to target, because also testing for these compounds is not easy and it's quite expensive. So that's also something that's going on at the regulatory level, trying to understand which of these compounds can we use as indicator compounds. Can tertiary nitrification, for example, be an indicator of pharmaceutical removal, as we showed from the plant in the UK? So I think from a regulation level, being able to understand that this is very complex and how are we going to monitor at that level is a challenge. And specifically to your question about the control and the percent removal, there's not really an online way to do that, right? We'll have to look at other ways of monitoring this, because we can't. There's not really instrumentation, right, available that would be able to give us this tool. But being able to design the systems, as Fernando described in the early part of the presentation, being able to engineer the systems in the right way helps us to know that we are getting that removal through the system. Anything else to contribute there, Fernando?
No, Brandy.
Okay.
There is one.
No, go ahead.
Yeah, how does this fare in comparison to mbbr technology? Any studies on it? I don't know if I understand the question, but
I think they're asking about micropollutant removal through mbbr technology. And to be honest,
sorry,
I'm not actually familiar with any studies. Veolia doesn't do mbbr technology specifically. I'm not sure if those people doing mbbr have done a lot of work on micropollutant removal, but mbbr is based on activated sludge technology, and the information that we showed you at the beginning of the presentation comparing activated sludge and biofilm technologies does give some indication that there's a preference for better removal with biofilm systems compared to activated sludge.
I was just saying we've probably got time for maybe 2 more questions, Brandy. Yeah,
there was a question on PFAS. And I mean, the short answer on that is we haven't been able to solve that biologically. It's just something that we haven't managed to do. I know everybody is very interested in that, but unfortunately, we at least have not been able to find a biological solution to the PFAS.
Yeah, they are not biodegradable. So that's, I think, it's understood that they are not biodegradable, these compounds.
Yeah.
Yeah, there was one interesting question about how do you measure diffusion limitation and ensure that biofilms are all healthy? Well, an interesting aspect here is that we are talking about very small concentrations of these pollutants. So the biofilms that we form are actually very thin. Even if we would use conventional carriers that may allow for very thick biofilm growth, it doesn't happen. And that's why Brandy was explaining the concept of providing more food or substrate, different substrate or carbon source, so that they can also grow. And the reason why also to provide this extra carbon is that it is believed that one of the metabolic paths of degradation of these micropollutants is co-metabolism with perhaps nitrification, for example. So the diffusion limitation shouldn't be a problem. Actually, again, my colleague Elena, they conducted studies with the Technical University in Denmark, where she did her PhD on the absorption of these micropollutants, and only a specific positively charged or micropollutants with positively charged groups would be more absorbable into the biofilm, but the absorption was actually limited for the rest of pollutants. So that shouldn't be a problem for biofilms in this case.
Try and do that. There was one more question there, which I thought was quite interesting. Can it be applied to drinking water?
That's a great question, but where we're actually looking, I mean, this right now what we're doing is looking at applying this at the wastewater treatment plant level. There would be a whole set of specific challenges with applying this at the drinking water plant that haven't really been examined, let's say, at this point.
But I would like to add that the potential of doing this for drinking water is there, absolutely.
Yeah.
We have implemented mbbrs for removal of ammonium, for example, from or nitrate from drinking water for specific sources. Also, there are studies being conducted actually in Australia for the removal of odor from universities in Australia in collaboration for the removal of odor from drinking water based on mbbrs. So the next step is also if there are the presence of micropollutants in drinking water that can be also removed with if not alone with mbbrs, in combination with other technologies.
Yeah.
Sounds very interesting and great. Well, thank you very much for your time this afternoon. It's a really interesting presentation. And so thank you again for your time this afternoon. And I'm sure you'll be able to find me. My name's Karen Shaw at Veolia if you want to contact me with any other questions or potential projects or ideas for where we might be able to implement this wonderful technology in Australia. So thanks everyone and take care. Goodbye.
Thank you.
Thank you. Goodbye.